Welcome back. In this lecture, we will talk about two-stage compression with water intercooler, liquid subcooler, and liquid flash chamber. Okay, so let's look at the schematic. So this is the schematic which we have here. So we have the evaporator. So in the evaporator, this is where you extract heat from the storage space, whether it is a food item that is being stored, or is it a room where human beings are there. Okay, so this is the region from which heat is to be removed. So that is my evaporator, and you can see that M1 is the amount of refrigerant that enters into the low pressure compressor. So once the refrigerant gets compressed, it enters into the water cooler. So in the water cooler, there is some sort of a cooling that takes place. And what is the cooling that is being done here? What is the intention? The intention is to de-superheat the refrigerant. So if you look at the pH chart over here, so the pH chart over here, so this is your point number 1, which is on the dry saturated state after leaving the evaporator. So you follow a constant entropy line, and when it is compressed, it reaches point number 2. So point number 2 is the state of the refrigerant after the compression in the low pressure compressor. Okay, and from there on, if you look at the water intercooler which we have seen earlier, the de-superheating happened in such a way that point number 3, it was lying on the saturated vapor line. But now you can see that the de-superheating happens only up to point number 3. So at point number 3, there is some sort of a de-superheating, but still the vapor is there on the superheated state. So that is your point number 3. Okay, so after point number 3, so here there is a junction. So this is a junction. So you can see that there is one refrigerant that is entering into this junction at condition 3. There is another refrigerant which is entering at condition number 9. You can, so if you look at the pH chart over here, so this is condition number 9. So there is one branch that is entering at 9. There is another branch which is entering at 3, and both of them mix together, and that mixing condition is what we call as 4. Okay, so 3 and 9, they join together and they arise, and there arises another new state point, which is point number 4. So it is at that point number 4, or at that particular condition, it enters into the high pressure compressor. Okay, so 4 is the entry to the high pressure compressor. Okay, so 3 4 and 9 4. Okay, so 3 and 9, they mix together, there arises a new point 4. And then in the high pressure compressor, there is again compression that takes place at an isentropic condition. So you once again follow a constant entropy line. So this line over here is also a constant entropy line. Okay, and then this is your compression that happens in the high pressure compressor. So 5 is the exit. 5 is the exit at the high pressure compressor. You can see that point number 5. And from point number 5, it enters the condenser. So for entering the condenser, you can see that M2 is the amount of refrigerant that enters into the condenser. If you look at the evaporator circuit, in this particular circuit, you can see M1 is the amount of refrigerant that enters the low pressure compressor. M2 is the amount of refrigerant that enters into the condenser. Okay, and so this mass flow rate that enters into the condenser, the refrigerant that enters into the condenser, it is condensed at point number 6. So at the exit of the condenser, you can see point number 6. So from 5 to 6. So this is a lengthy line. So this is 5 6. Okay, so from 5 to 6, I am fixing my point on the saturated liquid line at the pressure level of the high pressure compressor. Okay, and then we have a liquid subcooler where the refrigerant is subcooled to condition 7. Okay, so from 6, I am moving to 7. So this is my point number 7. Okay, and then from 7, it enters into an expansion valve. So you can look that in the layout over here. So the expansion valve, which is mentioned as E1. So the refrigerant which is subcooled, it enters into the expansion valve, it expands, and that expansion is shown here as 7.8. So since it is a throttling process where enthalpy is constant, H7 is equal to H8. Okay, and then there comes the flash chamber. So in the flash chamber, what happens is, see, there is the condensed refrigerant that enters, the refrigerant liquid that enters into this particular flash chamber. Okay, some amount of refrigerant, it evaporates in the flash chamber, vapor gets collected, and M3 is the refrigerant vapor that is generated in this flash chamber. And the purpose of using this flash chamber is, see, in the expansion valve, sometimes when the subcool liquid, when it expands, during the expansion process, when the temperature and the pressure drops, some of the liquid refrigerant during the expansion process, some of the liquid refrigerant, it becomes vapor. Okay, and that vapor need not be carried into the evaporator, because when a vapor enters into the evaporator, the heat carrying capacity for the vapor is less when compared to the heat carrying capacity of a liquid, because the liquid can undergo a phase change, and then for during that phase change process, heat can be extracted, and once the phase change process is over, when it is in the vapor state, it can be superheated and much more heat can be extracted. So whatever vapor that is being generated here in the flash chamber, so that vapor is being taken directly to the high pressure compressor. Okay, so the vapor is not sent into this particular, to the right hand side of the circuit. The vapor is taken back to the high pressure compressor. Okay, so you can see like, so that is where you have 8, 9. So that is this circuit. So let me change the color to show you that. So there is one exit over here, and this exit has a mass flow rate M3. So this is in the vapor form, and this vapor is taken to the high pressure compressor, and this condition is stated as 9. So from 8 there goes 9. So 8 to 9, which we show in the pH chart, 8 to 9, which we show in the pH chart, this is one condition, okay, where the vapor leaves the flash chamber. But there is another state from 8 to 10. So let me show it with, let's say green. So from 8, there is another condition called 10. Okay, and that is on this part. So from 8, there is 10. So at point number 8, there is another branching. One goes to 9, the other goes to 10. So this guy which goes to 10 is in the liquid state, and that guy which flows over here, that is in the vapor state. Okay, and then once again, whichever goes, the vapor which goes over here, so that is at condition 9, and as already stated, the condition 9 mixes with condition 3. So this is refrigerant vapor at condition 9, this is refrigerant vapor at condition 3. Both of them mix together at this junction, and it results in a refrigerant vapor at condition number 4. And that is what we have seen earlier. Okay, and now let's look at the other part of the circuit. From 8, it goes to 10. So that is refrigerant liquid. So 8 to 10, which I have already shown with a green color line. Then it enters the expansion valve 2, which is again an isenthalpic process or a throttling process where H10 is equal to H11. So that is the second expansion that is taking place. And this from 11 to 1, that is your evaporator, where heat is extracted from the region that needs to be cooled. Okay, and a few points which you can notice at point number 2. So when we solve the problem, so this is your point number 1. You follow the constant entropy line till you reach 2 over here, and then they would specify the condition at 3. Okay, so where you will have to look at the constant temperature line. So this dotted line which they have shown you here is temperature T3. So let me show it with some other color, say let's use black over here. So this line which they have shown that passes through 3, this is your constant temperature line T3. This is your constant temperature line T4. Okay, and similarly you can also see this is 7. This is constant temperature line. So this will be a straight line in the pH chart. So this will be your T7. So while solving the problem, we will look at this very clearly. Okay, so now in this particular two-stage compression, we have a water intercooler which de-superheats the refrigerant vapor that leaves the low pressure compressor. Then you have a liquid subcooler which subcools the liquid that leaves the condenser, and then the liquid flash chamber. I'm sorry, I have this word that is missing over here. So this is liquid flash chamber, the flash chamber where the vapor and liquid is separated. The vapor is taken to the high pressure compressor and the liquid is sent back to the evaporator. Okay, so this is the layout and the pH chart for two-stage compression with water intercooler, liquid subcooler, and liquid flash chamber. And before proceeding to the problem, let's look at these two specific conditions. One is the flash chamber. So if I take the flash chamber, I have a condition, say 8, that is entering in, and I have a condition that is 10, which is leaving, and I have another condition which is 9, which is also leaving. In this case, this guy which is leaving is a vapor, this guy which is leaving is a liquid, and what enters here is also a liquid. And what enters here is from the condenser, so the mass is M2. What goes to the evaporator has a mass M1, and what goes to the high pressure compressor is mass M3. And so the first mass balance equation is M1 is equal to M2 minus M3. This is the mass balance equation. Then if you look at the energy balance equation here, I have one entry and two exit. So M2 H8, that is the entry. So M2 is the mass of the refrigerant, liquid refrigerant that is coming in, and the condition is 8. So it is M2H8. This is equal to M3H9 plus M1H10. Okay, you can also call this as H11. H10 is equal to H11, and both of them are that is nothing but HF at the intermediate pressure PI. Okay, and so if you want to substitute for this M3, or so M2 times H8, M3 can be written as M2 minus M1 plus M1H10. So if you expand this, you will get M2H8 is M2H9 minus M1H9 plus M1H10. And if we further simplify by taking M2 on one side, M2H8 minus M2H9, and that is equal to M1 times H10 minus H9. Okay, and so my M2 is M1 times H10 minus H9 divided by H8 minus H9. So this is one definition, or the formula by which you can estimate the value of the mass of the refrigerant that flows through the condenser. So this is one branch point, which is the flash chamber. There is another branch point which is shown in the picture, where there is the refrigerant vapor M3 at condition 9 mixing with the mass of the refrigerant M1 mixing at condition number 3, and both of them uh, enter into the compressor with the mass flow rate M2 at condition 4. Okay, that is what is shown over here. So this point I am writing it down over here. So you have two entries with reference to this junction. There are two entries and one exit. So M2H4 is equal to M1H3 plus M3H9. And what I want to find out is the value of M3. So M3H9 is M2H4 minus M1H3. And I already know the definition for M2. Okay, so let me use the space. So M2 is M1 times H10 minus H9 divided by H8 minus H9. The whole thing is multiplied by H4 minus M1 H3. Okay, and if you want to find M3, this entire term should be divided by H9. Okay, so that would give you the mass flow rate of the refrigerant that enters into the high pressure compressor. Okay, so you have two branch points, and you can use those two branch points to and apply the energy equation, the energy balance equation at those branch points to estimate the mass flow rate of the refrigerants that is entering into the condenser and the mass flow rate of the refrigerant that is leaving the flash chamber, which is M3. Okay, so now let's solve a problem over here. A two-stage compression ammonia refrigeration system. It operates between the overall pressure limits of 2 bar and 14 bar. So if you look at the given details, the pressure of the evaporator, which is the lower pressure, which we call it as P1. So that is at 2 bar. The intermediate pressure, they have not mentioned it over here, so that is mentioned here as 5 bar pressure. So intermediate pressure is 5 bar, and then you have the condenser pressure, which is your 14 bar. Okay, what else is said here is the temperature of the superheated vapor and the subcooled liquid are limited to 30 degrees centigrade. So the superheated vapor and the subcooled liquid. So the superheated vapor is limited to 30 degrees centigrade, and the subcooled liquid is limited to 30 degrees centigrade, which means this temperature T7, the temperature, this is, let me change the color over here again. So the temperature over here, this is the subcooled temperature. So T7, this guy is limited to 30 degrees centigrade. And the superheated vapor, so 1 to 2, that is superheated. They are not talking about this 30 degrees centigrade. They are talking about the desuperheating that takes place, and still the vapor is saturated. So this T3, that is also equal to 30 degrees centigrade. That is what they mean. Okay, so T3 is 30 degrees centigrade, and T7 is also 30 degrees centigrade. The flash tank separates the dry vapor at 5 bar pressure, and the liquid refrigerant then expands to 2 bar. COP of the mission they want us to find out, and the power required to drive the compressor. If the mechanical efficiency of the drive is 80%, that's okay. That we can do it later on. So finally, we have to multiply it with 0.8. And refrigeration effect, they have given it as 10 ton of refrigeration. So 10 ton of refrigeration, 10 into 3.5, that is going to be 35 kilowatt. Or if you want it in kilojoule per minute, it is 10 into 210, so it is 2100 kilojoule per minute. Okay, so these are the given details. So now let's go to the pH chart of ammonia. So the operating pressures 2, 5, and 14. Okay, so the operating pressure 2 bar This is my evaporator pressure. P5, that is my intermediate pressure. And 14, let's say somewhere over here. So this is my 14 bar, which is pressure of the condenser. Okay, let's say 14 bar. Okay, so now if you look at this, so now I have to fix my point number 1 on the 2 bar pressure line. So travel on this 2 bar pressure line till it reaches the saturated vapor line. So that is going to be my point number 1. Then you have to follow the constant entropy line, follow the constant entropy line. Okay, and I have to go till it reaches the 5 bar pressure line. Okay, so I think that is my 5 bar pressure line over here. Yeah, so that is my point number 2. Okay, and then what they have said, you should superheat it till it reaches 30 degrees centigrade. These red color markings over here, 20, 40, 60, 80, those are the temperatures. If you want, let's say this 20, follow this 20 over here. So this 20 is 20 over here. And if you follow this line, you will find 20 over here. So this 20 is a straight line. So it's something like this. So if within the bell curve, so you have the constant temperature line like this. And then it drops. Okay, so this is how the constant temperature line is inside the bell curve. Okay, so we are following that. I need the space for writing the enthalpy value, so I have erased it. Okay, so now I have fixed my point number 2. So that point number 2 is on the 40 degree centigrade line. So now we need to desuperheat it till 30. So this is my 30 degree line. So this is 20, this is 40, and the intermediate line is 30. So this point over here is point number 3. Okay, and then I'm going to have point number 9. Point number 9 is on the 5 bar line. So that is on the saturated, dry saturated vapor line. So this is my point number 9. So I have to fix point number 4 between 9 and 3. Okay, so to find out that, I have to find out the other values first. So what are the other values that I can find out? So the final pressure is the 14 bar. So if you draw a straight line over here, so this is my 14 bar line, and the point over here. So I'll have 4 here, then I have to travel across the constant entropy line and fix it on the 14 bar. That will be my point number 5. So this is my point number 6. This is my point number 6. So from point number 6, let me put it a little bit higher. So this is my point number 6. And from point number 6, I have to go till the 30 degree centigrade line. So let me show it with a different color over here. So from 30, so this is the 30 degree centigrade line. If I draw a vertical line from 30, so I have to, so this is my point number 6 over here. From 6 to the 30 degree centigrade line, this is going to be my 7. Okay, so this point over here is my 7. Then from 7, I have to drop a perpendicular. This is not a perpendicular, I'm sorry. I have to drop a perpendicular till it reaches the 5 bar pressure line. So this is going to be my point number what? Point number 8. So from 8, I travel along this line. So this is my 8, 9. And then to the right, to the left side, this is my point number 10. Then from here, I have to drop another perpendicular till I reach the evaporator pressure. This is my point number 11. And from 11, I can reach point number 1. Okay, so the only missing link is my point number 5 and 6. Okay, so now how to find out point number 6? So before proceeding to that, so let's write down the enthalpy values. So from 1, if I drop a perpendicular over here, So that is between how much? So this line is 1400. So when I drop a perpendicular like this, so that is between 1400 and 1500, very closer to 1400. So H1, let's say 1420 kilojoule per kilogram. Okay, since I am using the chart which I am visualizing, okay, I am looking at it straight away, so my values can be erroneous. So I want you to do this on your own, and I'm pretty sure that your values will be completely different from what I am getting over here. Okay, so now if I drop a perpendicular from 2, so now that guy is between 1500 and 600, but it's uh, about the midway of 1500. So let's say 1560 kilojoule per kilogram. And point number 3, if I drop a perpendicular over here, that will be right here. And so that is, let's say 1530. And what else can I mark? H9. H9 is here. Drop a perpendicular from this. My line has deviated. So this is 1500 and this is 1400. So it's, let's say, is it midway? No, inclined towards 1500, say 1470 kilojoule per kilogram. So that is my H9. Okay, so once I fix my H9, now I can fix H6 and H8. H6 and H8, they are closer to the 300 value. So let's say 340. H6 and H8, they are 340 kilojoules per kilogram. Okay, and then let's say H10 and H11, they are very closer to 200, 210. H10 and H11, they are 210 kilojoule per kilogram. Now what I'm going to do is I'm going to use these values, okay, to find out the value of H4. So H4, for H4, where is the, so to find out H4, so H4 is this junction. Okay, we talked about this junction earlier. Let me use this green color over here. So I am worried about this place over here. So at this particular point, there is an entry at 3. There is another entry at 9. Okay, and then it leaves at 4. So I want to find out the condition 4. So I have to take this junction. So if you have to consider this junction, this is M1 times H3 plus M3 times H9, that is equal to M2 times H4. Okay, so let's write that. That's what we have written it already. So that is what we are going to apply it right now. Okay, so let me write it over here. So I have a junction. In that junction, I have entry at 3 with a mass M1, and I have an entry at 9 with a mass M3, and I have an exit which is at 4 with a mass M2. But now the question is, I don't know any of these masses, isn't it? So I have to first find out the mass M1. So what they have given us in the problem is refrigeration effect is how much? 10 ton of refrigeration, say 2100 kilojoule per minute. Okay, and can I find out the refrigeration effect from the enthalpy values which I have got? Yes, I can find out. It is H1 minus H11. So H1 minus H11. So H1 is 1420. H11 is 210. So it is 1210 kilojoule per kilogram. So if I want to find out M1, so that is nothing but 2100 divided by 1210. So how much is that? So how much is that? Let me calculate it. Let me use my calculator over here. So 2100 divided by 1210, that is 1.74 kilogram per minute. Okay, so that is my M1. So now I have to find out M2 also. So to find out M2, now I have to look at the flash chamber. So if you look at the flash chamber, for the flash chamber, there is an entry at the entry is at 8. One exit is at 9. The other exit is at 10, isn't it? So this guy is M2, this guy is M1, and this guy is M3. Okay, so what we have is M2H8 is equal to M1H9 plus M3H10. What we know is M1 is M2 minus M3, isn't it? M1 is M2 minus M3. Okay, so now we can substitute M3 as M2 minus M1. M2 minus M1 times H10. So it is M2 times H8 minus H10 is equal to M1 times H9 minus H10. So M2 is M1 times H9 minus H10 divided by H8 minus H10. So M1 is 1.74 kilograms per minute, and then H9 is what we found as 340. No, H9 is much lower. H9 is higher, 1470. 1470. H10 is 210 divided by H8. H8 is equal to H6. No, H7. I'm sorry about that. This guy is H7. Okay, so H7 is equal to H8, which is how much? 340. 340 minus 210. Okay, so let me calculate that. So 1.74 multiplied by 1470 minus 210 divided by 340 minus 210. So that gives me 16.86 kilograms per minute. Okay, and now I can write M3 dot is M2 minus M1 dot, because we have kilogram per minute. So M2 dot is 16.86 minus 1.74, which is 15.12. So this guy is 15.12 kilogram per minute. So that is your M3 dot. Okay, so now I know M3 dot. So now let's come back to this junction over here. Now let's come back to this junction. So for this junction, what we have here now? So what we have here is M1H3 plus M3H9, that is M2H4. And what I need to find out is the value of H4. So it is M1H3 plus M3H9 divided by M2. And because we have kilogram per minute, everything can be M dots. So M1 dot was 1.74. H3 value, let's look and write it. M3 dot is 15.12. H9, we found H9 somewhere over here. H9 is 1470 whole divided by M2 dot is 16.86. So what is the value of H3 which we have identified? Let's check 1530. So that is the value of H3, 1530. So now let's evaluate it using the calculator. So 1.74 into 1530 plus 15.12 into 1470 divided by 16.86. So that is 1476.19 kilojoule per kilogram. So this guy is 1476 approximately. So 1476, now we have to fix that 1476. So 1476 is very closer to, so this is my 1500. This could be 90, 80, 76. So let's say it is this guy over here. So this is my point number 4. If you want me to show it in another color, let me use black over here. So this is my point number 4. So once again, I have to take the constant entropy line till it reaches the 14 bar line. The 14 bar line we have already drawn using red. So let me complete it in black. So it starts from here. That is the 14 bar line. So this is my, say, point number 5. So point number 5, I drop a perpendicular from here. Say it is closer to 1600. So 1625 maybe, 1625. So H5 is 1625 kilojoule per kilogram. So now we have identified everything. The question is, they want us to find the COP of the mission. We already know the refrigeration effect. So now what we have to find out is the work done in case of the low pressure compressor. So that is going to be M1 dot times H2 minus H1. So that is what is going through the low pressure compressor. For the high pressure compressor, I have the mass flow rate M2. So M2 times H5 minus H4. So here we have, what was that, 1.74 H2 minus H1. Let's look at the values. 1560 minus 1420. 1560 minus 1420. So that is your value for H2 minus H1. M2 is 16.86. H5 just now we find that as 1625, and this guy is 1476.19. So these two should give us W, the work input for the low pressure compressor and work input for the high pressure compressor. So it is 1.74 multiplied by 1560 minus 1420, and that guy is 243.6. This guy is 243.6. It's not kilojoule per kilogram. This guy is in kilojoule per minute, because it is in kilogram per minute. Okay, so how about the next one? 16.86 multiplied by 1625 minus 1476.19. So that is 2508.94. 2508.94 kilojoule per minute. So the total work input is WL plus WH. So 243.6 plus 2508.94. So if you add it, I'll get 2752.54 kilojoule per minute. So now they have also given the mechanical efficiency. So 2752.54, multiply it with 0.8. So if I multiply it with 0.8, I would get, where is it? I should divide it by 0.8 because when I say the mechanical efficiency is 80%, the power input should be more. Okay, so 2752.54 divided by 0.8 is 34. So this is division. Divided by 0.8, 3440.68 kilojoule per minute. So COP, refrigeration effect, divided by power input. Refrigeration effect is 2100 and this guy is 3440.68. 2100 divided by 3440.68, so that is 0.61. So this is this COP. Okay, so that's all we have in this particular video lecture, and in the next video we will talk about three-stage compression. Thank you.